Welcome to BE544. In the previous lecture, we have covered the differences between binary classification and multi-class classification, and we mentioned that binary classification deals with two categories, let's say benign and malignant tumors, where multi-class classification deals with multiple categories such as the grading of a specific tumor. Then we discussed the loss function and which one to use based on the type of the classification, whether it's binary or multi-class classification. After that, we covered the meaning of label encoding, and we mentioned that there are two techniques, one-hot encoding and the label encoding. Also, we covered the differences between train-test split and cross-validation during the model evaluation process. And finally, we trained a simple CNN model and differentiated between multiple aspects like overfitting and underfitting. In today's lecture, we will mention again the differences between overfitting and underfitting, where overfitting happens when a machine learning model learns the details and noise in the training data, and in this case, it negatively impacts the performance of the model on the new data, which is the testing subset in our case. Also, this can happen when the model is too complex compared to the number of the observations or instances in our data. So we can say that the model can fit the training data very closely, but it cannot predict the new data. That's why it's reflected in the curve with a high performance in the training and low performance in the validation or testing. So we can say that the model is not generalizing to the new data, but instead memorizing the training data. On the other hand, underfitting happens when the machine learning model is too simple to capture the underlying structure of the data. In this case, the model performs poorly on both the training data and testing data because simply it fails to learn the patterns in the training data. And is reflected on the curve also when you find that the training and testing curves are very low, especially when you find that the validation or testing curve is a bit higher than the training curve. And in that case, we can say that the model is not flexible enough to capture the complexities of the data. There are multiple causes of overfitting, like using models with too many parameters, having insufficient training data, and including too many irrelevant features that can introduce noise in the data. On the other hand, underfitting can be caused when the model is too simple. This means that the number of parameters or features is not enough. So to mitigate both of them, there are multiple techniques that can be used, and it's not necessary that all of the techniques can work for all of the datasets. So simply, you need to try and find the most suitable technique that can help your model to avoid the overfitting and underfitting. So to mitigate overfitting, you can simply reduce the number of parameters, which are the trainable parameters, by using regularization techniques like L1 and L2, or simply lasso and ridge techniques. You can use also cross-validation techniques. So instead of depending on the training test split, you can switch to the cross-validation by using k-folds. You can use data augmentation to increase the diversity of the data. You can use also early stopping to halt the training process when the performance of the validation subset starts to degrade. And to mitigate underfitting, you will need to use a sophisticated algorithm or a model to increase the complexity of it, add more features to your model, reduce the regularization strengths if it's too strong, or train the model for more epochs to learn more complex patterns. So you can imagine it like a tuning process. Your aim is to find a high performance and fitted model. You may stuck in overfitting, so you can use any of the mentioned techniques to avoid it. And in that case, will move from being overfitted to a fitted model. And in some cases, you may apply multiple techniques to avoid overfitting, and it can lead to underfitting, which is the other issue. For example, you may apply regularization techniques with a high strength, and during the training, the overfitting is decreased, but it stuck into underfitting. So when you find an optimal value of the regularization strengths, you can also mitigate the underfitting So it's like a tuning process to find the optimal or reasonable values for your dataset and the problem. So our goal is to find and develop a robust model. So there is a specific balance between the overfitting and underfitting, which is also called bias variance trade-off, where underfitting reflects the high bias. This means that the model or the problem is too simplistic, and for overfitting, it can be reflected as high variance, where the problem is too complex or your model is too complex. So again, our goal is to find a robust and fitted model that performs well on the training and validation data and generalizes well to the new data, which we can assume it the testing subset. So let's cover the different techniques to prevent the overfitting. As mentioned, regularization helps to prevent and avoid overfitting, and hence will improve the model generalization. So regularization simply is a way to help the model by adding constraints or penalties to the learning process. There are two common techniques, L1 and L2 regularization, or lasso and ridge techniques respectively. For the L1 regularization or lasso technique, you are adding a penalty to the weights equal to the absolute value of the magnitude of the coefficients, and this reflected in this equation. So you are simply getting the summation of the absolute values of the weights and multiplying it by a regularization factor, which is the strength. And this is done during the calculation of the cost function. And again, the aim of the cost function is to help in the backward propagation to update the weights, aiming later to improve the training curve and performance. However, L1 regularization technique can lead to sparse models where some coefficients become zero, where we can say that this model performs feature selection. The second technique is called ridge technique or L2 regularization, where we are adding also a penalty, but here it's equal to the square of the magnitude of the coefficients. And this means that we are distributing the error among all coefficients. So also in the cost function, we are adding the square of each weight and summing all of them together and later multiplying it by the strength of the regularization and adding it to the cost function. You can also combine both L1 and L2 regularization, and it's called elastic net regularization, where we are balancing between the sparsity of the model and the coefficient shrinkage. So now you can try three techniques, L1, L2, and both of them, which is called elastic net. Another technique is called dropout, and this technique simply is used in deep learning, where during the training process we are randomly selecting neurons to be ignored for what's called dropped out. And by following this approach, we are preventing the network from becoming too reliant on particular neurons, which this can help promote the robustness and prevent overfit. This graph compares between the dropout or the training and inference phases or the testing phase. So during the training process, we are dropping out some neurons randomly, and this happens in the hidden layers. So if you have a dropout rate, let's say 50%, then we are dropping 50% of the neurons in the hidden layers randomly. And this random process happens every epoch. So 50% of the neurons are dropped randomly during each epoch. This will ensure that the model will not memorize which neurons were dropped out. But in the inference phase or the testing phase, all of the neurons are active. So this means that the dropout layer works only in the training phase. This graph also shows a roadmap to balancing the models to avoid overfitting and underfitting. So simply, if you are here and got a fit model, then you don't need to apply any other techniques. However, if you stuck in the overfitting, then you need to try different techniques to mitigate that, or a combination between them, like decreasing the model capacity or the number of parameters, add and apply the regularization techniques, and you can also increase the strength of the regularization. Perform feature selection in case that you are manipulating the features during building your model, adding more training data in your dataset. Also, if you are stuck in the underfitting path, then you need to increase the complexity or the capacity of the model or your feature set, reduce the strength of your regularization technique, or you can also remove any regularization layers in your model. You can increase the model complexity, and you may also decrease the number of training data by finding any outliers in your data and drop those instances. So again, our goal is to find the optimal model generalization. A third technique that helps to prevent overfitting, which was reflected here by gathering more data, is called data augmentation. And simply, gathering new data, especially if you are dealing with medical data, can be challenging because collecting data and obtaining them following the ethical path can take more time. So, a technique that can be followed to increase the diversity of your data is to use data augmentation, where we are artificially increasing the size of the training data by applying image processing techniques like rotation, shifting, shearing, zooming, and so on. A fourth technique is called patch normalization, where each layer is normalized to have a mean of 0 and a standard deviation of 1, and this will help to stabilize and accelerate the training process. So instead of getting a collapsed distribution of the data like that, we are switching to a mean of 0 and a standard deviation of 1, so the data is spread along the axis, helping the model to stabilize. Another technique is called noise injection, where we simply add random noise to the input data or the weights during the training process. And this will help also prevent the network from relying too heavily on specific patterns and forcing it to generalize better. Gradient clipping is another technique where you are setting a threshold to gradients during the backpropagation process in the training process to prevent exploding gradients. You can also utilize ensemble techniques like bagging, posting, and stacking, where we are combining predictions from multiple models to improve the robustness and generalization. So think about that like you are developing multiple models which are different, and you are fusing the output or stacking the probabilities after the flattening or applying the average pooling layer, where each model can capture specific patterns, and this can lead to improve the robustness and generalization. Again, it's not necessary to apply all of these techniques. You are selecting one or two techniques or trying one by one or a combination of them until you reach a fitted model or the most suitable technique which effectively reduces the overfitting. So regarding the data augmentation technique, this graph visualizes the most commonly used image transformation techniques. So if there's the original image and you applied a rotation up to a specific rotation degree, let's say 10 degrees, then you are selecting a random value between -10 and +10, and based on that value, you are rotating the original image. So let's say that we rotated the original image by +7 and -9. Then in this case, we got two artificial slides or patches alongside the original one. So now we have three images. Also, you can apply a shearing up to a specific percentage, let's say 15%. And by applying shearing horizontally or vertically, you are obtaining a new version of the original image. You can also shift in both width and height, where you're shifting or changing the position of the image horizontally or vertically. You can also apply zooming, where you are zooming in the original image, and in that case, you are obtaining also artificial versions of the original image. You can apply horizontal and vertical flipping by flipping the image horizontally or vertically. And not all of the techniques should be applied, as some of the techniques contradict with the medical assumptions. For example, you may need to use vertical flipping in the histopathology data, as it may change the cell orientation. You can also mention that I'm not using horizontal flipping and vertical flipping, as they are going to change the orientation of the cells in the histopathology data, where the orientation, for example, is a strong factor to differentiate between the categories or the grades of a specific tumor. There are many other techniques that you can utilize for the data augmentation, not only applying transformation and obtaining artificial versions from the original image, but you can also apply techniques that generate synthetic data from your dataset, like utilizing a model called GAN, or Generative Adversarial Network, where you can utilize it to generate synthetic data and use the data alongside your original subset. But it's important to note that data augmentation should be applied only to the training data. And you must apply that also after splitting the data into training, testing, and validation subsets. Because if you split the data after data augmentation, there is a high probability that one of the augmented images appear in the validation or testing, and its original version is in the training subset. So as a point, data augmentation should be applying after the split and only to the training subset. Now we need to apply these techniques to our model to avoid overfitting and obtain high performance. So for that aim, we are going to utilize a public dataset. It's called Breast Cancer Histopathological Database, or BREAK-HIS in short, where this dataset is split first into two categories, benign and malignant. And for each category, there are 4 other subcategories. So for the benign, there are 4 subcategories and another 4 for the malignant category. And the authors of this dataset has exported different cases, and for each case, there are multiple magnification levels: 40x, 100x, 200x, and 400x. And these are samples from the 4 categories of the benign category. And now we need to utilize this dataset and apply our model on it and learn which techniques is going to work on this dataset to obtain a high performance. And this dataset is simply used in many research articles in the literature. So once you obtain a specific performance, you can compare your performance with other researchers or articles, aiming to get an indicator about your performance, whether you are close to them or you are far away from their results. So again, as a reminder, in the previous lecture, we got overfitting, and we mentioned that because there is a big gap between the training accuracy and the validation accuracy, and our aim now is to train our model and obtain better performance. So let's go to script number 11, where we first imported the different packages. And as a recap, this was the simple CNN model that we utilize in code number 10, where we now need to modify that model by adding dropout layers inside that model, aiming to prevent the overfitting and judge whether the dropout layer will help to mitigate the overfitting or not. So we created another function called simple CNN dropout, where it accepts the input shape, number of classes, the optimizer, and whether to propose the model summary or not. In the structure of the model, we added a flatten layer and followed by a dropout layer with a 50% dropout ratio. Also, we added another dropout layer after the dense layer with also 50% as a ratio. And because we have 4 classes in our dataset, let's say we are dealing with the benign category, which includes 4 subcategories, then we are adding here 4 because we are getting 4 classes, and hence we are using the softmax output activation function and use that layer if the number of classes is more than 2. Otherwise, use the dense layer with the sigmoid output activation function. And if you need to make it generic, simply change the value of 4 to be exact to the number of classes. Here, we checked also if the number of classes is more than 2, then we will use categorical cross entropy, and otherwise use the binary cross entropy for binary classification. So this function, which is called simple CNN dropout, is generic to binary classification and multi-class classification. And for the metrics, we are doing the same. We will use binary accuracy if the number of classes is 2, and otherwise it's categorical accuracy. After that, we started dealing with the BREAK-HIS dataset. So this block, which starts from here to here, is related to the Breakheads dataset or the dataset that we mentioned in the slides. So if you have another dataset that you are going to use, then you need to format this block appropriately to work with the new dataset. The aim of this block is to read the file names and paths of the images and split them into training, testing, and validation subsets, preparing them for the training process. So here we define which category to use and which magnification to use, the classes names, and the base path. So if you extracted the Breakheads dataset after downloading it from this website, from here, by clicking on the link, you will find the structure is as follows. The data is inside the breast folder, inside the histopathology, the histology slides, inside Breakheads version 1, where it's split into two categories, benign and malignant. Here we are selecting the benign. And then you will find a folder called SOP, where the subcategories are inside it. So first we checked if the path is correct or not. If not, it will raise an exception. Otherwise, we are going to read the paths of each category. So we are looping on each category from the list here and getting the absolute path of each category in the dictionary. And if any of them doesn't exist, it will raise an exception. Then we created a loop to loop on each class and get different cases in each class. And then we looped again on each case and got the images in each case depending on the magnification level, because you will find in each case that there are different magnification levels as mentioned. And then we got the absolute path of the image and appended it to our X list and the name of the class into Y. So now we have X and Y, where X is a list that holds the paths of the different images and Y holds the corresponding labels. We didn't read the images in this phase as we did in script number 10, because we are going to use a class from TensorFlow that will read them efficiently, but to execute it, it needs the paths of the images and labels as a data frame. So we created a pandas data frame that contains image paths column and labels column. Then we split the data frame into training, testing, and validation using the train test split function. It got the data frame and the test size, which is 20%, and we applied stratify to ensure that the split among classes is equal. Now we got the train and test data frames. We split again the train data frame into training and validation. So now at this moment we have train, test, validation data frames, and each of them contains two columns, one for the images paths and one for the label. Next, we defined the configurations of the experiment, the input shape, the batch size, the number of epochs, and where to store the results. We mentioned that we are going to use those data frames using a specific class from TensorFlow, and it's called image data generator, and it accepts different parameters. And for now, we will use only the rescale, because this class can be also used with the data augmentation, but for now we will not apply data augmentation. And rescaling here will normalize the pixel values. Instead of being from 0 to 255, it will be normalized to be in the range of 0 to 1. Then we use the function called flow from data frame, where we passed the train data frame to get the training generator and defined the X and Y columns. X should be the paths for the files or the images, and Y should be the corresponding labels. And because we are using multi-class classification, we mentioned here that we need it to be categorical. We define the batch size, the input shape for resizing, and to shuffle the training data. We created another generator for the validation and a third for the testing. We did the same, but here we used the validation data frame, and we did the same for the testing, but we used here the testing data frame. For visualization purposes, we have created here a plot for each portion, the training, validation, and testing, where when executed, it will generate 3 images, 4x4, which reflect 16 samples randomly selected from the generators. And this will show you if the generators are working efficiently or not. Now we created an object from the sample scene and dropout function using the optimizer Adam. The number of classes, which is 4. Purpose is 1 to print the model structure and the input shape. We used the fit function, and in that case, the fit function will accept the train generator instead of passing x and y explicitly. We set the epochs and the batch sizes. Also for the validation data, we passed the validation generator. We created the callbacks, and in that case, the model will start training and the output history will be stored in the history object. For the history object, we will use it here to plot the loss and accuracy curves for the training and validation. And also here, we will print the metrics after executing the evaluation on each generator, training and validation and testing, aiming to get performance metrics on each subset. And don't forget to load the best models before evaluating or predicting. After that, we generated the confusion matrix using the predict function and got the true and predicted labels, created the confusion matrix and displayed it as a figure. When you execute that, you can get summary like that. The layer type, the output shape, and the number of parameters, where this is the output layer, and those are the trainable parameters. After training for the 200 epochs and generating the curves, these are the metrics. Those are for the training, those are for the validation, and those are for the testing. And as you see, that the training accuracy reached more than 96%, but the validation accuracy stopped at 71 and testing stopped at 76, which is reflected on the figure like that in the training process. So as there is a gap between the training and the validation, we can say that there is an overfitting issue. It was more than that, or the gap was more than that before applying the dropout, but applying the dropout helped to reduce the overfitting. Also, you need to judge if the model applied early stopping or not, and you can judge that if the last epoch is not equal to the maximum number of epochs. So we have 200 epochs and the model trained for 200 epochs, so the early stopping wasn't executed. And this is the resultant confusion matrix. And we mentioned that our aim is to obtain more values in the diagonal because these are the true positive for each category. For example, there are 20 instances for the adenosis, which are correctly predicted to be adenosis. And also, there's a structure of the output folder where you will find the log file resulted from the CSV logger. You will find the curve which resulted from plotting the history, the confusion matrix, the best model, and the samples from each subset for visualization purposes, and the TensorBoard folder. And we will discuss that after a while. And we will discuss the aim of that folder after a while. Now we need to apply data augmentation alongside the dropout to check whether the model is going to improve or not. So the code will be similar to code number 11. The only change will happen in the generator by adding the configuration for the data augmentation. And this will be added only for the training subset. So for the validation and the testing, they will remain the same. So what we added here is a range of rotation up to 10 degrees, positive and negative. And for the shift, it's up to 15% for the width and height respectively. And the same for the shear, up to 15%, and the zoom up to 15% zooming in. We applied horizontal flipping and we didn't apply vertical flipping. And in case that the generator needs to create new pixel values, it will use the nearest pixel values to fill in the newly created pixels after transformations. So after executing this code, these are the obtained results. In case of the dropout, this was the curve. There is an overfitting here. And when we added data augmentation alongside the dropout, the early stopping is triggered because we stopped at around 130 or 125. So the early stopping is executed. Also, the performance didn't reach more than 71 or 72 in the training, and there is some sort of overfitting. So if you are going to compare between both systems, whether dropout only is better or dropout and data augmentation is better, we can say that dropout performs better than combining dropout and data augmentation. And this is what we mentioned. It's not necessary that all of the techniques will reduce overfitting. You can apply a specific technique that can perform badly compared to the original performance. One more point, you may change these values and obtain better performance. So this means that you need also to select the optimal values for the data augmentation, because increasing or decreasing a specific value in the transformation can confuse the model to distinguish between the categories. Maybe the horizontal flipping confused the model from distinguishing between the categories based on the orientation, and you may try turn off the horizontal flipping by changing the true to false, and you may get better performance. And you can get an insight in that case that horizontal and vertical flipping should be disabled for this dataset. Now let's assume that you obtained a good model and reasonable performance, and there is no overfitting in that case. So what's after? So what we are doing is training a model on the training data or the data we retrieved, so that later we need to use that trained model for the prediction and inference phases, where we should only use the best tuned model or a checkpoint and use the predict function to predict the new instances. So to do that, you can use script number 13, where we define the path of the image that you need to get its prediction, the model path where the best model is stored, the categories list, and the input shape. And then you simply read the image and transform it in a suitable format for the model, where first we converted from being BGR to RGB, resized it, applied normalization, and prepared it for the batch prediction using the predict function. Then we loaded the model, but first we checked if the model exists. If not, exception will be raised. Load the model using the model path, which is here, which in this case the best model. And if there is an issue during the execution, an exception will be raised. Then we got X to be predicted, and this is our prediction. In case of binary classification, we have only labels 0 and 1. And in case of multi-class classification, we have an index for the prediction. So we got the index that reflects the high probability using the argmax of the probability vector. And based on that index, we got the class name. Then we plotted a figure to display the image alongside the probabilities for each category. So simply we are not training here. We are just loading the model, reading the image, applying the prediction, and some visualization. So when you execute that code, you will get something like that. There's the input image that we assume that we don't know the actual label for it. And there's the predicted probabilities for the different categories. And as I loaded an image from the adenosis category, I'm sure that the model predicted it correctly. But in the inference phase, you don't know the actual label. So based on the prediction here, you are reporting the category with the highest probability, which is here, which is adenosis in our case. Now let's cover what is TensorBoard. You will find a TB folder in your experiment, and this is used for the TensorBoard. TensorBoard is simply a way to visualize and provide the different tools needed for machine learning experimentation. And simply to use it, you need to install it using the pip command, pip install TensorBoard, and using the command window, you can execute TensorBoard -- log directory and specify the directory that contains the TensorBoard folder. So let's assume that we need to apply the TensorBoard on the TB folder here. So simply ensure that the TensorBoard is installed by pip install TensorBoard is executed. Then write the command TensorBoard -- log directory and specify the directory of the TensorBoard like that. Now it will search for the TensorBoard folder and will run the server so that we can use it. As you see, there is a server which is HTTP localhost 6006. Using any browser, you can navigate to localhost 6000, where you can find the different tools for the training process. For example, you can find here the epoch categorical accuracy. You can toggle the font size from here to get the different values for each epoch, as you see in the bottom. You can also apply smoothing for the curve. By decreasing the smooth, it will be like discrete values, and increasing the smoothing, it will appear like a smoothed line for better visualization. You can do the same for the loss function, for the learning rate, for the AUC values, and so on for others. You can do that for the training and the evaluation as well. So simply you can get the evaluation curve, the evaluation loss, as you see here. So in this lecture, we have covered the differences between underfitting and overfitting. We covered multiple techniques to mitigate overfitting and underfitting. And we mentioned that our goal is to get a generalizable and fitted model. We used the Brickhouse dataset, where we applied dropout technique and data augmentation, and we discovered that based on the selected configuration for the data augmentation is that the data augmentation experiment performed badly compared to using only dropout. Finally, we covered what is TensorBoard and how to use it as a tool to help us investigate the history of our model.